Lesson 5.2, Verifying Trigonometric Identities. Now, prior to this lesson, you need to make sure that you've gone through Lesson 5.1, the fundamental trig identities. This lesson is about using those fundamental identities and putting them into practice. The goal here is going to be to verify identities. Now, the fundamental identities don't need to be verified. Those, I either went through the explanation in the last video as to why they're true, or we're just going to accept them to be true as basic facts of trigonometry. And one big thing of mathematics that we like to do is we take basic facts and use those to build new facts. Now that's what this lesson is all about. Take those basic facts and use them to prove other things to be true. Now, if you don't memorize those fundamental identities, this section becomes much more difficult. So if you don't have those identities memorized forwards, backwards, inside out, upside down, in other words, if I asked you what cosine was equivalent to and you couldn't give me 1 over secant, sine of pi over 2 minus theta, or possibly even for cosine squared, 1 minus sine squared, right off the top of your head, then you are not ready for this lesson. If you have to keep looking back at what identities you have available to you, then this lesson is going to be a waste of your time. Go back, memorize those identities, and once you know them forwards, backwards, inside out, and upside down, then proceed on to this lesson. Now, verifying an identity is similar to taking the word love and turning it into the word math. But the trick is you're only allowed to change one letter at a time, and every time you change a letter, it still has to be a word. In other words, anytime you apply a mathematical property, your new result still has to be a true statement. So, for example, I could take the word love. If I changed one letter, how about changing L into an M? Which changes the word love into move, which is still a word. I changed one letter, and that still produced a valid word. I could keep going. I could change the V into a T. Move becomes mote. Mote becomes moth. And moth becomes math. So one step at a time, each time I change something, it's still true. But you may have noticed at right here, from here to here, we could actually have gone a completely different route. Instead of changing mote to math, we could have changed mote to mate, and then gone from mate to math. So this points out simply that when we're verifying identities, there can be multiple ways of getting to the same destination, multiple ways of being right, and thus your way and someone else's way may have been different, but you're both absolutely correct. Now, problem with that is you may go a different route, and that might take you 4 or 5 more steps to get to the same destination that someone else got to in 4 or 5 steps fewer. In general, the shorter solution is considered to be the more elegant solution and the better solution, when in fact they're both equally valid. One can be considered better than the other. Now we can do it algebraically as well. We looked at this particular identity in section 1, and I explained how this was an identity versus x squared minus 1 over x plus 1 equals 0 was not an identity. Now we can verify this identity pretty easily using basic algebra. Now pay attention to the notation that I use when I'm verifying an identity. First thing I do is identify where I'm starting. I'm going to start with the left-hand side, and my goal is to manipulate the left-hand side using algebraic properties until it looks exactly the same as the right-hand side. Notice what I'm not going to do, what I'm absolutely not going to do, is move things from the left-hand side to the right-hand side. We are not solving, we are verifying, which means manipulate this until it looks like that. Once it looks like the right-hand side, I'm done. So the way I always start is I label left-hand side equals whatever the left-hand side was. I haven't changed anything. I am simply telling the reader I am starting with the left-hand side. Now hopefully you notice that x squared minus 1 is a difference of squares. This is a technique that's going to come up over and over and over again, so make sure you're looking for it. X squared minus 1 can be factored into x plus 1, x minus 1. Now you may notice that x plus 1 is on the top and the bottom, which means we can cancel it out. And when I cancel it out, we're left with x minus 1, which coincidentally, is the right-hand side. As soon as I have manipulated the left-hand side to a point where it looks like the right-hand side, I write RHS and I'm done. I have verified that the left-hand side is equal to the right-hand side through these algebraic manipulations. That's all verifying is. Now, it's not required that you write reasons off to the side like you did in geometry. You can just show your work, and that kind of suffices. Now, the goal here is for verifying trig identities, and the problem with verifying identities is that there is no set of steps that you can follow and get it right every single time, like there is, for example, with solving equations. If it looks like this, then you do that. If it looks like this, then you do that. With verifying identities, it's pretty much try something, see if it works. If it doesn't, try something else. Now, there are a few techniques that tend to come up over and over again, so I'm going to go ahead and list those out for you. For number one, start with the side that looks more complex. It's much easier to manipulate something ugly and simplify it versus to take something simple and, here's me making up a word, complexify it. Throughout elementary and middle school, you learn techniques for simplifying arithmetic expressions or algebraic expressions. We don't really teach techniques for making things more complex. That's not our goal. Our goal is to take something complex and make it simple. So that's something that you should think about here. If the left-hand side looks more complex, start with that side. If the right-hand side starts more complex, start with that side. It doesn't really matter which side you start with, as long as you simplify it into the other side. Also, work on only one side at a time. Again, this is not solving equations. This is verifying identities. We don't work on one side and move things from one side to the other side. We don't add to both sides of the equation. We don't subtract. We don't multiply. We don't divide to both sides of the equation. We only work on one side at a time. We manipulate only on one side at a time. So make sure you are not applying properties that are true for opposite sides of an equation, but not for the same side of an equation. For example, when you're dealing with a fraction, it's perfectly legal to multiply top and bottom by the same number. It is not legal to add top and bottom by the same number. That is never legal. That's legal when you're doing it on opposite sides of an equation, not top and bottom of a fraction. Don't get confused by misapplying properties. Now, if you run out of ideas on one side, you're more than welcome to jump to the other side. All right. What I mean by that and how it doesn't conflict with technique number two, let's say you're trying to get from point A to point B. Well, you can travel all the way from point A to point B if you want, or you could travel halfway from point A to point B and then have point B back up to meet you where you left off. All right. So in other words, don't move things back and forth like you would do with solving, but you can simplify the left side to a point. And if you run out of ideas, then you can jump to the right side and try to simplify that to the same point that you stopped on the left side. At no point, though, do you move things back and forth. Now, here's what you should really be paying attention to. Look for opportunities to. I'm going to list out some options. Factor or FOIL. This comes up so often. You got to be looking for opportunities to factor or to FOIL. In other words, to multiply through. For example, if I see 1 minus cosine squared, all right, you might recognize that as one of my fundamental identities. That's actually a Pythagorean identity. 1 minus cosine squared would equal, hopefully you just said sine squared. If you didn't say sine squared, then you are not ready for this lesson. Go back and memorize your trig identities. But you might also recognize that 1 minus cosine squared is in fact a difference of squares. 1 is really 1 squared, and of course this is cosine squared. If I have a difference of squares, in other words a squared minus b squared, then it can always be factored into a plus b, a minus b. So in that case, anytime I see that Pythagorean identity in its subtraction form, whether it be 1 minus cosine squared, 1 minus sine squared, or one of the other ones, secant squared minus 1, secant squared minus tangent squared, cosecant squared minus 1, cosecant squared minus cotangent squared, any of those Pythagorean identities that are being subtracted are all difference of squares and can be factored as such. So 1 minus cosine squared would really be 1 plus cosine, 1 minus cosine. Now you might ask yourself, well, how would I know to do that as opposed to simply replacing 1 minus cosine squared with sine squared? And that simply has to do with beginning with the end in mind, looking a few steps down the road. One of the techniques that I'm going to have in this list is going to be always keeping your target in mind. All right, if you know what you're going to have to do a few steps from now, then you're more likely to make the correct decision here. Now, of course, the alternative is, let's say you make the wrong decision. Let's say you take 1 minus cosine squared and replace it with sine squared. That may be correct. It may take you down a completely different road, and you may end up at the correct solution anyway, or you may not. All right, it's up to you to start thinking a few steps ahead to realize two things are equally valid, two steps are equally valid. Will both get me to the correct solution, or will one lead me to a dead end? And if you end up at a dead end, that's fine. Just stop, go back to where you had that decision, and go the other way. It doesn't mean give up, it just means back up and try again. Adding and subtracting fractions. For example, sine over cosine plus cosine over sine. Hopefully you remember that when you are adding fractions, first thing you have to make sure is that you have a common denominator. This one does not have a common denominator. I've got cosine and sine. Now, back in elementary school, one of the things you learned on how to get a common denominator is to look at the numbers you're given, for example, 1 over 3 plus 1 over 5, and ask yourself, is there a number, a least common multiple between 3 and 5? So then you would list out multiples of 3, 3, 6, 9, 12, 15, 18, 21, and you list out multiples of 5, 5, 10, 15, and then you would realize, hey, 15 is a common multiple of both, and you could use 15. But of course, the quicker way, in order to not waste time, is just take the 3 and the 5 and multiply them together. 3 times 5 is 15. Common denominator is 15. And then you would manipulate each of the fractions. On this one, you had to multiply top and bottom by 5 because, again, it's perfectly legal to multiply top and bottom of a fraction by the same number. On this one, you would multiply top and bottom by 3, so that gives you 15 as your common denominator. This would produce a 5, this would produce a 3, and then you could add them together. 5 plus 3 obviously being 8. But we're not dealing with numbers here, we're dealing with expressions, algebraic and trigonometric. That's irrelevant. It's still the same process. Now you may notice that when I multiplied the denominators, that actually caused me to multiply the numerators by the opposite denominator. For example, 1 got multiplied by the 5, this one got multiplied by the 3. So we kind of have a shortcut when we're adding fractions. This works 100% of the time. To get the denominator, as I said, just multiply the two denominators together. This one would give us BD. And then to get the numerator, we just cross multiply. D times A, B times C. And of course, if this is plus, then we add them together. If this is minus, then we subtract them. So this works every single time we are trying to add fractions together. Kind of a quick way to add fractions together. Take the denominators, multiply them together, and then to get the numerator, cross multiply. Sine times sine is sine squared. Cosine times cosine, cosine squared. I've now taken these two fractions and turned it into a single fraction. If I'm looking at an identity and I see the left side has two fractions but the right side only has a single fraction or no fractions at all, then that tells me that somehow I need to add those fractions together to replace them with either a single fraction, which could probably then be reduced further. Creating a monomial denominator. Keep in mind, monomial, mono means one. So a monomial denominator is a denominator with only a single term on the bottom. This one right here would be a binomial denominator. We've got a 1 and we've got a sine squared. We have two terms in the denominator. 1 minus sine squared, hopefully again you recognize that just like you did earlier. Well, isn't that just cosine squared? Yeah, it's cosine squared. By using the Pythagorean identity and replacing 1 minus sine squared with cosine squared, we have taken the binomial denominator and turned it into a monomial denominator. Now before, when I had the difference of squares here, I factored it out. Alright, that might have been useful on this one. It might not have been useful on this one. But by replacing it with the Pythagorean identity, that allows me to take that fraction and turn it into not a fraction anymore. Now of course it's still a fraction technically, but we're going to ignore the fact that it's over 1. The point is I could take 1 over cosine squared and replace it with secant squared because that's a reciprocal identity. Now hopefully you're not saying, hey, couldn't I have just taken 1 over 1 minus sine squared and flipped it in the beginning? And you would be absolutely incorrect, because the reciprocal identity applies to cosine, it applies to sine, it applies to tangent, it applies to only if it's a monomial denominator. You cannot take a binomial or a trinomial or multiple terms on the bottom and just move them to the top. That is illegal. You cannot do it. That's why we replace 1 minus sine squared with a monomial, which we can then bring to the top as its reciprocal. As I said earlier, keep your target in mind, plan ahead. You need to be thinking 2 to 3 steps ahead at all times. If you know what your destination is and you're thinking a few steps down the line at all times, then you are much more likely, when you're presented several options, to make the right decision. If all else fails, convert everything to sine and cosine. Every single one of your identities, every single one of your fundamental identities has some relation to sine and cosine, whether it be through a reciprocal identity or one of the tangent identities. For example, tangent is sine over cosine, cotangent is cosine over sine. So tangent could be turned into 1 over cotangent, but it could also be turned into sine over cosine. So if you don't really have any ideas and you're not really sure where to start, just convert everything to sines and cosines and then use algebraic and arithmetic manipulations in order to clean it up. Now, I say this as if all else fails. In other words, by converting everything to sine and cosine, that often will make the problem much more difficult than it had to be. If you are always looking for opportunities to factor, opportunities to replace something with an identity, that can often get you to your destination quicker than if you convert everything to sine and cosine. There'll be an example later on where I show you how if we notice one thing, then we can do it in 3 steps. If we convert everything to sine and cosine, we can still get to the same destination, but it may take 15 to 20 steps. So if you can't think of anything, convert to sine and cosine, but always try that as a last resort. Do something. There are 23 fundamental identities that you have memorized. There is absolutely no excuse for staring at a problem and not knowing what to do. There is something there. It's black and white. All you have to do is try it. Now, if you know what you could do, but you're not sure what you would do after that, okay, so do that one thing and then look at it again. Often it's easier to see what to do when it's written down in front of you than if you're just trying to plan it out in your head. I say plan ahead, but sometimes it's hard to see where you're going. If there's a bend up the road, it's not always possible to see around the corner, so get up to that bend and then look around the corner. If you think you know what you can do first, but you're not sure what you can do second, do that first step. Maybe that will make it more obvious what your second step is going to be. If you're staring at a problem for more than 10 seconds, just convert to sine and cosine. If you ever have a problem, you're not sure what to do, more than 10 seconds staring at a problem, convert to sine and cosine, go from there. And then make me a sandwich. All right, let's look at our first example. There's going to be 14 of these examples altogether. They are posted on Parent Access. The example handout is posted on Parent Access, so you can follow along on there, kind of work ahead if you want. Otherwise, you can just work from here. Keep in mind, you can pause the video at any time if you want to work out a problem on your own and then hit play to see how I did it. Now, I also, again, want to point out there are multiple ways to do these problems. Maybe the way I did it is not the way you did it. Your method may be correct. You're more than welcome to come talk to me at any point and ask me, hey, is what I did here correct? And I'll look through it real quick and I'll say, absolutely, that is correct. And it's either going to be better than my solution or it's not going to be better than my solution. But correct is correct, whether it takes 3 steps or 50 steps. So this one we are verifying an identity. Cosine of, that's the Greek letter beta. Cosine of beta times tangent of beta equals sine of beta. Now, proper notation, I'm going to start by labeling the side that I'm starting with. And it looks like the left-hand side is more complex than the right-hand side, so I will say LHS for left-hand side equals cosine beta tangent beta. Now I'm going to try to think of any type of identity that I can replace either cosine beta or tangent beta with, keeping in mind that my goal is to reduce this down to sine of beta. And hopefully you have recognized that tangent by the quotient identity is really sine over cosine. And by replacing tangent with sine over cosine, just like the algebraic example earlier, the cosine, one's up top and one's down below, they can cancel out and leave me with sine of beta, which of course is my right hand side, which means I'm done. I have verified this identity. The left hand side equals this can equal that, the cosines can cancel, which leaves you with sine, and that's my right hand side verified. Let's look at example 2. Once again, I'll start with the left hand side. Cosecant over secant. My goal is to convert it to cotangent. Now, keeping the target in mind, cotangent is really cosine over sine. Secant and cosecant are directly related to cosine and sine by reciprocals. So what I can do here is realize, well, cosecant is really 1 over sine. Secant is really 1 over cosine. And when I have a fraction divided by a fraction, I can keep it, change it, flip it in order to clean up the fractions. Now, I'm never really going to do that. That's really a waste of time. That's something you do in elementary school and middle school. All right, we are in a pre-calculus class. Feel free to skip those useless steps. Cosecant is the reciprocal of sine. If cosecant is the reciprocal of sine, then you're more than welcome to just take the cosecant, move it to the bottom, but of course when you move it across a fraction bar, it becomes its reciprocal. So cosecant moved across the fraction bar becomes sine. Same thing with secant. Secant moved across the fraction bar becomes cosine. So I can just take these two guys, flip them, and replace them with their reciprocals. Secant moves to the top as cosine, cosecant moves to the bottom as sine, and that right there is the quotient identity for cotangent. Example 3. 1 over tangent squared plus 1 equals cosine squared. Once again, I'll start with the left-hand side. I recognize that I have a fraction on the left-hand side, but I don't have a fraction on the right-hand side. So somehow I have to get rid of this fraction. I also have that addition problem there, that tangent squared plus 1. I don't want an addition problem. There is no addition on the right-hand side. So then I think about it for hopefully less than half a second, and I realize tangent squared plus 1 is one of my Pythagorean identities. Again, if you are not recognizing the Pythagorean identity, you were not ready for this lesson. Go back to lesson 1 and memorize your identities. Tangent squared plus 1 is secant squared, and of course secant squared is the reciprocal of cosine squared, so I can just, like I did before, move secant squared to the top and replace it with its reciprocal. Example 4. Cosine squared minus 1 over cosine minus 1 equals cosine plus 1. You might recognize that this looks exactly like that algebraic example we did earlier. I recognize I have cosine squared minus 1, in other words, a difference of squares, and I have cosine minus 1, in other words, a factor of that difference of squares. So I can start with the left-hand side, factor out the numerator, cosine minus 1, cosine plus 1. The cosine minus 1's cancel out. That leaves me with cosine plus 1, my right-hand side. Now again, back to the beginning, cosine squared minus 1 almost looks like a Pythagorean identity. The Pythagorean identity would have had to have been 1 minus cosine squared. So it actually would have been legal to take that cosine squared minus 1. Let me get my writing utensil. Actually, let's get a different color. It would have been legal to replace that cosine squared minus 1 not with sine squared, but with negative sine squared. Had you recognized the Pythagorean identity, cosine squared minus 1 is negative sine squared. So I would have had negative sine squared over cosine x minus 1, and then I would have realized that got me nowhere. Alright, so that's the point I'm trying to make. Sometimes factoring is the answer, sometimes replacing with the Pythagorean identity, like I did on example 3, is the method you want to choose. Alright, without looking a few steps ahead, you're not going to know which one is the right method. Now, if you're really not sure which one is the right method, try something. If I had tried this one first, I would have realized, yeah, that got me nowhere. go back and try something else, factor it out, that got it done for me. So if one thing doesn't work, try something else. All right, let's look at the next example. All right, let's prove that sine of b over tangent of b equals, that's a joke. I'm going to move on. Here's another joke. I'm just going to let you sink this one in. Moving on. All right, example 5. All right, I want to verify secant squared of y minus sine squared of y equals secant squared of y, times secant squared of y equals 1. All right, once again, I'm going to start with the left-hand side, but this one is this one and the next one are ones where all of them have had multiple options if you can realize what those options are. These next two, example 5 and example 6, really have some pretty good multiple options. What I mean by that is really you could go one way, I could go the other way, and they're just about the same number of steps. Although I think on the next one, converting to sines and cosines may not be the best move on the next one. But let's look at this one. Let me show you one way to do this one. All right. Now, most likely, when I present this to students first, the first thing most people think of is let's just convert everything to sines and cosines. For example, secant is 1 over cosine. This secant is also 1 over cosine, and this sine is already sine, no need to change it. So most students, when they first are presented with this problem, will convert the secants to 1 over cosine. Now, of course, over here, we've got sine squared times 1 over cosine squared, which is really the same thing as saying sine squared over cosine squared. Now, a couple of different ways I could go on this one. One option is to say 1 minus sine, since they have a common denominator, I can subtract and say 1 minus sine squared is 1 minus sine squared over cosine squared. And then 1 minus sine squared, of course, that's the Pythagorean identity, which is cosine squared, which reduces now to 1, my right-hand side. Now, converting to sines and cosines wasn't too bad. That's how far I got. Now, I'm going to back up just a little bit and notice right here there was a different way I could go, and I wonder if you noticed it. This sine squared over cosine squared, well, isn't that tangent squared? Oops. And the 1 over cosine squared, well, as we knew before, that's just secant squared. Now, had I left that secant squared alone and just converted the second secant squared, which reduced into tangent squared, I would have gotten secant squared minus tangent squared, which itself is an identity, and that identity equals 1. I would have gotten to my right-hand side in about two fewer steps, simply by leaving that one alone, converting that one to cosine, and aiming for the Pythagorean identity. Not something I would expect you to recognize right off the bat. Converting to sines and cosines worked just fine for us. There was no problem there. But let me go ahead and show you. I would call that option 1 and option 1.5. Let me go ahead and show you option 2, which I think is an even better option than either of those. And that has to do with recognizing secant squared, secant squared. I've got a binomial here. Here's one term, here's the second term, and in this binomial, each of those terms has a secant squared. Remember, one of our techniques was to look for opportunities to factor. I can factor out secant squared. Out of this binomial, I can pull out secant squared, and when I pull out the secant squared on the second term, it will just leave sine squared. On the first term, it will leave a 1. In other words, pull out the secant squared, I'm left with 1 minus sine squared. Well, 1 minus sine squared, once again, Pythagorean identity, cosine squared. And of course, I know the relationship between secant and cosine. They are reciprocals. So if I replace secant with 1 over cosine and multiply through, I would get 1. That technique is the one I prefer for this particular problem. In other words, if there's an opportunity to factor, take it. Converting to sines and cosines will get you there as well, but this got me there quicker. Factoring will get the job done quicker than converting to sines and cosines. Let's look at example 6. Tangent squared secant squared minus tangent squared equals tangent to the 4th. All right. Now, hopefully that you've every other problem you've been pausing to try these on your own. If you have not been doing that, shame on you. Go ahead and pause here to try this one on your own first. All right. So tangent squared, secant squared minus tangent squared. Again, I'm going to start with option 1. I'm going to show you one technique, and then I'll show you another technique on the same problem. All right, let's start with the left-hand side. Tangent squared, secant squared minus tangent squared. Now, just like on example 5, my first thing I recognized was the common factor in the binomial. I can take that tangent squared, factor it out. That leaves me with secant squared minus 1, which is a Pythagorean identity that equals tangent squared. Tangent squared times tangent squared equals tangent to the 4th. Done. 3 steps, factoring, quickest way to get there. But not the only way to get there. Let's try something else. Option 2. I think this is the one where all right, option 2. On this one, I'm not yet going to convert to sines and cosines. I'm going to show you another option that instead of factoring applies kind of the same steps but in a different order. Instead of factoring and then applying a Pythagorean identity, I'm going to apply the Pythagorean identity first and then multiply through. In other words, secant squared is 1 plus tangent squared. 1 plus tangent squared, if I distribute the other tangent squared, becomes tangent squared plus tangent to the 4th. Hey, that minus tangent squared cancels the first tangent squared, gone, gone, and we're left with tangent to the 4th. All right, so applying factoring techniques and Pythagorean identities is going to get the job done the quickest possible way. But again, there's still a third option. I could always convert to sines and cosines. Tangent is sine over cosine, secant is 1 over cosine, tangent is sine over cosine. Now we've got a problem here. It's still a binomial. Here's my first term, here's my second term. But I don't have a common denominator. On the left, that really says cosine to the 4th. On the right, it says cosine squared. So in order to get that common denominator, I could do what I did before and multiply across on the bottom, or I can realize I really only have to tack on an extra cosine squared top and bottom on the right side. So instead of using my more general fraction technique, I can just get my common denominator by fixing the right side. So that cosine squared becomes cosine to the 4th, and we have sine squared, cosine squared on the top. Common denominator means I can subtract, but here I might get stuck if I'm not always looking for opportunities to factor. I've got sine squared and sine squared, which means I can factor out a sine squared. Now, of course, if I'm going to recognize at that point that I can factor out sine squared, why didn't I just recognize the tangent squared at the very beginning? And that's where you start to realize, well, this whole thing was a waste of time. 1 minus cosine squared is sine squared. Sine squared and sine squared is cosine to the 4th. Sine to the 4th over cosine to the 4th equals tangent to the 4th, right-hand side. You see how long that took converting to sines and cosines? Look for a better opportunity. All right, here's another one that you can go ahead and try. All right, so hopefully you have tried this one and you are seeing how well you did. Left-hand side, secant of pi over 2 minus, that is the Greek letter phi. Anytime you see this piece right here, you should be thinking cofunction, which means secant can be turned into cosecant. I don't have anything I can factor out, so I think the only option here is to convert to sines and cosines. But again, you could convert everything to sines and cosines, or you can be thinking ahead a little bit. My goal is 2 secant. I want to get to 2 secant. Right now, I've got this term right here, and I've got this term right here. In other words, I already have 1 secant. I don't need to do anything to this secant. I just need to turn this guy into secant, and then add secant plus secant to give you 2 secant. So I'm going to convert to sines and cosines, but I'm only going to convert it on the first term. I'm going to leave that secant alone because it's done. I'm going to bank it. I'm going to put it off to the side and forget about it. So cosecant is 1 over sine. Tangent is sine over cosine. Secant, not doing anything with it, just leaving it alone. Look at that, the signs cancel. You're left with 1 over cosine. And hey, isn't 1 over cosine equal to secant? So secant plus secant equals 2 secant, right hand side. Tangent plus cotangent equals secant cosecant. All right, here's one where I'm going to look at it for a second. I'm going to start with the left-hand side. I know I have to add these two terms together because there's no addition on the right side. And I'm going to quickly run out of ideas other than just converting to sines and cosines. So that's what I'll do. Tangent is sine over cosine. Cotangent is cosine over sine. And hey, if you go back to our suggested techniques from the beginning of the lesson, this was one of the examples I gave you. And it combined into this. Cosine times sine is my denominator. Cross multiply for the numerator. Now, sine squared plus cosine squared, again, hopefully you recognize sine squared plus cosine squared equals 1. And now I have 1 over cosine sine. My goal is secant cosecant. Well, those are reciprocals. This is not an addition problem. This is a multiplication problem. It's perfectly legal in a multiplication problem to simply take well, you can really think of it as 1 over cosine theta times 1 over sine theta. You can't do that with an addition problem, but because it's a multiplication problem, it's perfectly legal to think of it like this, and then to replace each of these individually with secant and cosecant. But normally I would just say, hey, if you've got cosine on the bottom, bring it to the top. If you got sine on the bottom, bring it to the top. Secant, cosecant. It only works because it's multiplication, right-hand side. All right, once again, I'll start with the left-hand side. Hopefully you've noticed that pretty much all of these problems I have designed to make sure that you start with the left-hand side because I like to be consistent. No reason that I always have to start with the left-hand side, I just always do. 1 minus tangent of x squared. And if you are saying that 1 minus tangent x squared is 1 squared minus tangent squared, then you are absolutely wrong. You will always be wrong. Stop doing that. When you want to square a binomial, you cannot just square each term. You multiply it by itself. Squaring means take whatever's on the inside and multiply it by itself. In other words, you have to FOIL this out. Look for opportunities to factor and FOIL. So 1 times 1 is 1. 1 times negative tan is negative tan. Negative tan times 1 is also negative tan, which gives me 2, or negative 2 tan. And then negative tan and negative tan is positive tan squared. So by FOILing it out, I get my quadratic trinomial, 1 minus 2 tan plus tangent squared. If you are looking ahead, keeping your target in mind, you realize, hey, I'm looking for negative 2 tan, and it's sitting right here. Just like on that secant example prior, that negative 2 tan is part of my destination, so I'm going to take it and I'm going to move it to the end of the problem. Negative 2 tan, I'm going to move off to the side, which brings the positive tan squared closer in. So in other words, I'm just switching these two terms, which is perfectly legal in an addition problem. But I moved it off to the side because, of course, negative 2 tan is part of my goal. It's part of my right-hand side. I'm done with it. I'm going to leave it alone. I'm going to ignore it from this point forward. And then I realize 1 plus tangent squared. Hey, what's 1 plus tangent squared? It's secant squared, which is my right-hand side. I'm done. All right, once again, we've got two fractions, 1 over 1 plus sign plus 1 over 1 minus sign equal to 2 secant squared. I don't have any fractions or addition over here, so I know I need to take this left-hand side, get a common denominator, and add them together. Remember to get the common denominator, we're just going to multiply straight across on the bottom, 1 plus sign, 1 minus sign, and then we're going to cross multiply on the top. So in other words, I have the 1 minus sign right here, which was multiplied right here. And then I have the 1 plus sign right here multiplied in this direction. And 1 plus sign, 1 minus sign on the bottom, if I were to FOIL that out, if hopefully you recognize difference of squares, that's the factorization of the difference of squares. A plus b, a minus b would be a minus b squared, 1 minus sign squared. And of course on the numerator, negative sign, positive sign cancels out, you're left with 1 plus 1 equals 2. From here it should be pretty straightforward. 1 minus sign squared is really cosine squared, and cosine squared can be brought to the top as secant squared, right hand side. All right, this one looks very similar to the last one. Go ahead and pause here and try it on your own. All right, just like I said, so very similar to the last one. We'll start with the left-hand side. We'll get our common denominator and cross multiply to turn it into secant plus 1 plus secant minus 1 over secant x minus 1 secant x plus 1. Foil through on the bottom, you get your difference of squares, secant squared minus 1, and of course the 1's cancel out on top, you get 2 secant. Secant squared minus 1 can be replaced with tangent squared, and here's where we start to get a little iffy. Now remember, my goal was 2 cotangent cosecant, 2 cotangent cosecant. So I'm going to jot that down up here, 2 cotangent cosecant, just so I remember what it is I'm looking for. Now I've got the 2 is done, but I don't want secant or tangent squared. I want cotangent and cosecant. I also don't want a fraction. So what I'll do is I'll go ahead and take this tangent squared and I'm going to bring this upstairs as a cotangent, but just simply because of the order of these terms, instead of tacking it onto the end, I'll go ahead and squeeze it in up here as 2 cotangent squared secant. All right. Now again, my goal is to manipulate this cotangent squared secant into cotangent cosecant. I've already got the 2 that I need, and if I realize cotangent squared is really cotangent times cotangent. So not only do I have the 2 that I need, I have the cotangent that I need as well. This stuff is done. This is banked. I need to manipulate this to turn into cosecant. And I can do that pretty easily simply by converting to sines and cosines. Cotangent is cosine over sine. Secant is 1 over cosine. Cosines cancel. 1 over sine. Cosecant. Right hand side. Alright, now we're on to the last 3, 12, 13, and 14. And these 3 are all going to involve a similar technique that most likely you probably wouldn't guess to do it unless you had seen it before. Alright, now I'm going to start with that left-hand side. I'm going to go ahead and deal with these negative t's by realizing these are just even and odd identities. Cosine is even, which means I can ignore that negative. Sine is odd, which means I can't ignore the negative completely, but I can ignore it right here and simply move it to the outside. So I have cosine of t over 1 minus sine t. Now, my goal is to have the 1 plus sign on the top. Right now I have 1 minus sign on the bottom. So I need a technique that will not only change that 1 minus into a 1 plus, but will also flip the fraction. And that technique has to do with conjugate pairs. 1 minus sign has a conjugate pair. Conjugate means 1 minus sign turns into 1 plus sign. And it's perfectly legal to multiply top and bottom by the conjugate, and that's a technique that's going to come up over and over again. It's a technique that came up way back in the beginning of the course. If you want to get rid of something, a binomial on the bottom, multiply by its conjugate. So that's what I'm going to do. That gives me cosine times 1 plus sign on the top, and 1 minus sign and 1 plus sign, of course, conjugate pair, difference of squares, 1 minus sine squared. I do that so that 1 minus sine squared becomes cosine squared, which then cancels with the cosine on the top, leaving me with 1 plus sine over cosine, right hand side. And again, this is one of those techniques that if you hadn't seen it before, you would probably have never have guessed to do that, but now that you've seen it, that's another technique you need to be looking for. If you want to turn a fraction upside down, try multiplying by its conjugate. Alright, let's look at this one. We'll start with the left-hand side. I've got an addition problem. I got to get rid of that addition problem because I need to turn that addition into a fraction. Well, let's turn these into fractions by converting to sines and cosines. Good news, these terms have a common denominator of cosine, which means I can add them together, and now I realize, hey, this looks exactly like the last problem. Let's multiply by the conjugate to reverse the order. Difference of squares up top. Don't distribute on the bottom because we know that cosine is going to cancel once I take that 1 minus sine squared and turn it into cosine squared. Cosine cancels, Leaves me with cosine over 1 minus sine, right-hand side. Last one. Immediately I see the cofunction right here. I'll go ahead and fix that cofunction into a sine. And then I realize once again, hey, these look just like the last example and the one before. I'm probably going to be using a conjugate method on this one. But let's recognize something before we do anything else. You might also want to say, hey, let's add these fractions by multiplying the denominators and then cross-multiplying on top. Don't do that. That would actually make the problem more difficult than it needs to be. Recognize 1 plus cosine over sine is part of my final answer. Just like we've been doing all along, if you have part of your final answer done, don't manipulate it any further. Bank it. Put it off to the side. Forget about it. My goal is to get to 1 over cosine, or 1 plus cosine over sine. I already have one of them. I wonder where the second one is going to come from. So really my goal is simply to take this first term, flip it upside down, I'll use the conjugate method, and then add them together. That'll give you 2 of them. So I'll take that sine over 1 minus cosine, multiplied by the conjugate, 1 plus cosine. That gives you a difference of squares on the bottom. Notice I'm not doing anything to that second term. It's just going to come all the way down. 1 minus cosine squared is sine squared. The sine cancels out. We're left with 1 plus cosine over sine. Add it together. 1 plus cosine over sine. Final answer, right-hand side. All right. Now again, verifying identities is not something that you can just observe and hope to be successful at later on. You have to practice this. You have to practice this a lot. The way you get good at this is by practicing it over and over and over again and realizing, hey, what's in front of me is something that I've seen before. Maybe I can try that technique that I've seen before on this one. If it doesn't work, try something else. There are plenty of techniques to try. Sometimes it may take you a page and a half to realize that the best option would have been to do something different on step 1, but that's just the way the cookie crumbles. The more you practice at this, the better you get at it, just like every other type of mathematics.